So worksheet 9B, these are your notes on specific, mostly it's on Newton's law of cooling, which is a very awesome application of an exponential function. We are going to be solving these as accurately as we can, which means we are no longer going to take the graphing approach for most of these questions. We're going to be taking a straight algebra solving approach. So on the tests and homework questions, like, I should say work. So it can't be one of those, I did it on my calculator things. No, you're going to have to show me work. You're going to solve it very specifically, and rounding becomes a factor when the question is addressed where, like, you want the value to be over or under a certain amount. We have to be careful how we're rounding the final answers. Now, this almost worked out perfectly. It would have been awesome if I could have taught this to you right before Thanksgiving, because these questions are all about products coming out of a heated device and cooling off. Like your turkey. This would have been a perfect turkey calculation. You know, didn't you all use Newton's law of cooling when you took your turkey out of the oven? No? Well, you probably gave your family salmonella poisoning or something. So the examples that we're giving are a little lame. It's like taking a cake out of the oven. Your precious coffee cooling to the perfect temperature. Like, no, you're not going to pull out a Newton's law of cooling calculation to determine whether your coffee is hot or cold enough, because you're probably just going to burn your tongue on it and live and learn. So, but you have to understand that there are many, many applications in the industrial sector for these. And I have a close to my heart example of my father works as a mechanical engineer technically, but his company makes, I think we've talked about this, really large furnaces for airplane parts. And a big part of their calculations is when they have something coming out of a heat-treated furnace, they have to thusly cool it down. And how do you cool down that metal? Well, think about metal, guys. If you heat it up and then subsequently cool it down, if you don't do that appropriately, do you think that might affect the brittleness or sustainability of the metal? And if you then realize that his company is making furnaces that treat airplane parts, do you think it's important if they cool it down appropriately? Probably, because when you're up in an airplane, you really hope it doesn't fall apart. So, you know, do we submerge it in a warm water bath? Are they going to use a different type of ventilation in their furnaces? You know, how are they cooling down these materials, and how long does it stay in this medium? That's part of their calculations. But we're not ready for that, guys, because y'all haven't gone to college yet. So we are going to be doing problems that involve my two loves, baking a cake and cooling coffee. I think Mrs. Hoffbauer wrote these just for me. Wasn't that nice of her? All right, there's two formulas here, guys. They're the same formula, but the one that we're going to be using is the one that's a little bit further down the page. This guy right here. That is Newton's law of cooling. So let's talk about what these variables represent. This is a very sciencey formula where they use subscripts. So T sub F is the final temperature of your product. So if you have a target temperature in mind, that's what they're talking about. T sub S is the temperature of the surroundings, but I will warn you on your test, they often call that T sub M for the temperature of your medium, because surroundings and medium are the same thing in this application. For a cooling a cake question, you're just going to let the cake cool in the air. But like there's an example coming up where you're cooling a hard-boiled egg, and that's often put into a cold water bath. So the surroundings would be at the water in that case. Let's see, T sub naught, anything sub naught is initial or original, so it's original temperature. K is a constant for that product in that environment. It has a constant value for cooling. And then T, of course, is time. So these problems are a little annoying, and that's your teacher telling you that. Yeah. So they have two parts. There's scenario part 1, where you're going to find the constant of cooling, and then scenario part 2, where you're going to use that constant of cooling to figure out how long it's going to take for your product to get down to the desired temperature. So I just want to warn you that you're going to have part 1 and part 2 in this question. So first example, Newton's law of cooling, a cup of coffee. Aw. It has cooled from 92 degrees Celsius to 50 degrees Celsius. So this number right here, this is your initial temperature. Starts off at 92 degrees Celsius. And then for part 1, they want your final temperature to be marked at 50 degrees. And then it says in a room of 22 degrees Celsius. This is the air temperature, so that's the temperature of your surroundings. Sometimes, again, you'll see T sub M instead of T sub S. And then there's another clue snuck in here, guys. It says it took 12 minutes for that to happen. So that's your little lowercase t that represents time. So for part 1 of our calculations, we're going to use all those clues and we're going to be able to find k. All right, here we go. So formula starts off with T sub F. So final temperature, which is 50, minus the temperature of the surroundings, which is 22, equals, make sure this next part is in a quantity, a parenthesis set. Initial temperature was 92, minus the surroundings, which was 22 again. You're going to multiply that by E raised to the negative k times t power. So for us, that would be negative k times 12 power. So that's the setup, and that looks really gross, but I think we can simplify this quite a bit. Like for instance, right here, 50 minus 22 is what, 28? And then 92 minus 22 is 70. Times e to the, instead of writing negative k times 12 power, most humans would just write that as negative 12k. Okay, so this is where all your practice this weekend is going to come into play, guys. How do we solve this equation? Well, we're going to need to apply a logarithm, but not yet, because first you have to isolate the base. Okay. Oh, thank you. So first, let's divide both sides by 70. And this is where, depending on how much work you're writing down or how much truncation you're willing to forfeit, like this is just about a cup of coffee, guys, so I'm not really that worried about accuracy in the long run. It's not like we're going to kill somebody with a hot cup of coffee. So if you went ahead and rounded this to like the 100th place, I think we're okay. But for me, because I'm lazy, what I usually do is I go ahead and I apply the natural logarithm right now. So if I apply the, and why did I choose natural logarithm, by the way? It's a base e, very good. So if I apply a natural logarithm to both sides of this equation, over here on the left side, I just get some gross number. Could you please type that in and tell me what that is? Give me like 3 decimal places. But on the right side, the natural log and e cancel, and you just get negative 12k drops down. I have no idea what that number is. I did not write it down ever. What's the natural log of this? Something negative? Negative 0.916-ish. Yeah. And we're truncating, so like 3 decimal points is good. Thousandths place is fine. All right, divide both sides by negative 12. And you just found your constant of cooling, which is called K. And it should be approximately 0.0... I rounded weird. Is it 0.07 or 0.08 when you round on yours? 0.08? Okay. So, what we're going to do now, that was just part 1 of our calculations. Now we have to do another question, a follow-up question. This is part 2. And this time, we know K. This time we're going to find little t. So almost everything is the same. You still have the same initial temperature. So we're going to pretend like the problem starts all over again at the beginning. Initial temperature is the same. The surroundings are the same. But a big difference here is your final temperature is now going to be 30 degrees instead of 50 degrees. So here we go. So instead of 50 minus, we're going to start off with 30 minus 22. 92 is still your initial temperature. And then up in the exponent for your base e, remember we found k, and this time I don't know t. So it's negative, and then k, which is 0.08, times t. So since we have a different target temperature, now we are going to have a different time. All right, so everything else is the same. You're going to simplify, divide, apply the natural logarithm, so that's all good. Let's see, 8 equals 70 times e to the negative 0.08 t power. I'm sure you're going to divide by 70 on both sides, and at this point again on your math, if you want to write down a decimal on your work, that's fine. But what I'm going to do is I'm just going to go ahead and apply the natural log to that fraction. So on the left side, I need to know what the natural log of 8 over 70 is. Give me like 3 decimal points, or places. Thank you. And then over on the right side, natural log and e will cancel, so you just have negative 0.08t. And then one more step, divide by negative 0.08. I will give you a little word of advice on calculating t, especially when you get to your test on Friday. Or calculating k, excuse me, on the first part. Your k value through your calculations should come out to a positive, like a small positive decimal, because in the formula it's e to the negative kt power, so the decreasing is already incorporated into the question. So if you're going through your calculations for k, and you end up with either a number that's not tiny, or you end up with a negative answer for k, that means you've messed up somewhere. So go back and figure that out again. What'd you get for time here? Is it like 28 something? I don't know. See, when I originally did this, I rounded really weird, so truncation could cause me a problem. What is negative 2.169 divided by negative 0.08? 27.11? Okay. And then my label on this was minutes. So fun fact, by the time you calculate this, your coffee is probably going to be cooled. And it is. Look at that. I even went, remember how I wasn't supposed to drink coffee? Thanksgiving broke me. All right, so this question, something else near and dear to my heart. A cake. It's removed from a 350 degree oven, and it cools to 120 degrees after 20 minutes, and the room is 65 degrees. So that's part one calculations, is just you finding the constant of cooling for the cake. And then we're going to come back, and we're going to figure out when is your cake cooled all the way down to 90 degrees. Now, as the classroom baker in here, I'm going to tell you, if your cake is 90 degrees, you can't frost it yet. I don't know why you'd wait till 90 degrees. You need it way cooler than that, people. You ever tried to frost a cake this hot? Frosting slides right off. Don't do it. All right, part one, let's calculate. So part one is just to find K. All right, so this is your initial temperature. It comes straight out of the oven at 350. And then our first part, the final temperature for the first part of our calculations is 120. 20 minutes is T. And the surrounding medium is 65 degrees. All right, here we go. So 120 minus 65 equals, make sure this next part's a quantity. It's 350 minus 65. And then e to the, where are we at? Negative 20 times k power. Because it'd be negative and then k times t. I just rearranged it a little bit. All right, little simplification here. Oh gosh, that's 50. Is that 55? Okay, equals 285. Excellent mental math, Abruzzo. E to the negative 20k power. Divide both sides by 285. You either get a gross decimal or you leave it as a fraction. Now would be a great time to apply which logarithm? Natural log. Okay, I need some calculation help because I don't think I rounded in a good way. Someone tell me what they get when they divide or apply the natural log to 55 over 285. Thank you. And then e and natural log will cancel, so you still have negative 20 times k. Divide both sides by negative 20 real quick. So we'll call it 0.08. Sounds good to me. So it's a small positive number, so I'm feeling good about that. And now that's just part one, remember. That was the first part of the calculation, was to find k. Now we got to go back and we got to find how long it will take for the cake to cool to 90 degrees starting from when you took it out of the oven. So one of the major changes in this next part is your temperature that's final is going to be 90 degrees this time. almost everything else is the same, with the exception of now I know K, but I don't know T. All right, so so remember K is 0.08, so the formula is e to the negative kt power, so negative 0.08 times t. Alrighty. Little calculation here, that's a 25. And we said that was a 285 last time. Times e to the negative 0.08 t power. So you're going to divide both sides by 285. And it's up to you whether you change that to a decimal or keep it as a fraction, because your next step is going to ask you to apply a natural logarithm. All right. Left side, gross decimal. What you got? Thank you. And then on the right side, natural log, base e, those are going to knock out, and you just have 0.08t. And divide both sides by negative 0.08. And above all else, I mean, I know we kind of make up these questions so they're not always super realistic, but they're semi-realistic. If you get an answer that doesn't make any sense to you, then stop and think about what maybe went wrong in your math. What do you get here for t? What was that? I'm sorry. All right, so roughly 30.4 minutes. Which, you know, you're cooling, what are we cooling this time, a cake? Cooling a cake. I mean, that seems logical. If I did my math and it came out to like, 587 minutes, like, I might stop and think about that a little bit. Alrighty. Questions. I know those aren't super fun. The good news is you only have to do one of them on a test. The bad news is you have to do a bunch for homework. You look happy. Alright. This question is asking about a half-life. So this is one of the formulas. It's a little different on this paper, but it's like the formula that's on your pink card. I want to bring your attention back to your pink card, though the formula I'm referring to is this guy, n equals n sub naught times r to the t over h power. That's the formula that they give you on the pink card, which is the one you get to use on the test. So remember, n sub naught is just the initial amount. The r is the growth or decay factor, like 1 minus the growth or decay, little r. So for this question, when it says it's a half-life, they're referring to your population size halving every so many years or minutes or whatever it is. So for our question, 1 minus half is 1/2. So that guy right there is going to be a 1/2. What if it says doubling? A 2 would be your base. Very good. So I just bring that to your attention because maybe I just keyed your exams that you're going to take on Friday. Maybe you have to know both. Okay. So half-life would be half and doubling would be 2. So this question, how much will remain? Okay, keep reading. We have a radium-226 isotope. The half-life is 1600 years. So they know through some previous calculations that this is H. They start with a 120 milligram sample. So for their formula, they're calling it P. For our formula, we call that n sub naught. And then how much will remain after 4,000 years? So that's how much time is going to go by. Our formula calls that T, their formula calls that X, but it means the same thing. It's going to go through a couple of half-lives, so it halved itself and it halved itself again, and then it halved a little, or almost halved again. All right, so let's do the calculations here, guys. This is just in the home screen of your calculator, but there will be a question on your test where it's all about like you setting it up and finding it that way. So get used to setting things up, especially for your homework and subsequently your test here. We have a 120 gram sample. It's halving, and then to the T, which is 4,000, divided by 1600. So on your home screen of your calculator, you can just calculate that for me. Everyone, please practice typing that. And it doesn't tell you really where to round, so I don't know. Let's go to like the 100th place. That's always safe. You should be getting 21.21 milligrams. If you don't get that, we gotta talk about why. So, Another question that I could and will ask you on your test is, now that you've set up your formula, can you use your algebra skills to predict when a certain amount will occur? So we're no longer relying on our graphing calculators to find approximations. We're not going to use our graphing calculators to like find intersection points. We're going to be using straight up algebra skills. So this time it says I want 10 milligrams to remain at the, like as a final amount for the product. So that number is going to go actually at the beginning of the formula. That's our target. So 10, and you're still going to start with the 120 milligrams. R you could write as 0.5 or 1/2, I don't care. But remember this time they change the parameters of the problem, so you don't know T. But the half-life of the isotope is still 1600. Okay. So using our skills from the previous lessons, I'm solving this exponential equation by first isolating the base. So first thing I need you to do is divide by 120. So you've got, was that 0.083 repeating or something? Okay, so this is, let's go ahead and just accept some decimals here. I'm okay with truncation, guys. So we have 1/2 to the T over 1600 power. Now a little bit of bad news. I mean, Newton's law of cooling was kind of gross, but at least it had a base E. This one does not have a base E. It doesn't even have a base 10. So you can technically apply any logarithm you want, and neither one's going to be any better, except we all know natural log is better. So I'm going to apply a natural log. While nothing cancels, what does happen? Why did we have to apply the natural log? Or a log, I should say. This exponent, yep, gets located down in front now. So you have, like, whatever the natural log of 0.0833 is, equals, and then this T over 1600 is now down in front of the natural log of 1/2, which is something gross. So, guys, I'm trying to solve for T. Now it's a game of moving terms around. So you're going to divide both sides by the natural log of 1/2. I need to hear lots of clicking here. Everybody practice typing these. Nothing worse than getting to game time on the test and you don't know how to type something. And I still have one more step, guys. I have T divided by 1600. So this is going to be some weird decimal. What's my final step to solve for T? I have to multiply by 1600 at the end. And it should be a pretty significant number, right? Like something in the thousands. I don't know. 5. That sounds right. One more time. Did you say 44? 45, thank you. And again, you know, these are all like about answers because I don't know how accurately we're measuring this isotope. So that's a little tour of how they use carbon dating, because if they have an isotope that they can measure, they can figure out, because they know the half-life of it, and they can determine how old something is. What did I do wrong?
Oh, no.
Oh, yes.
On the test, if we have like a couple numbers off or stuff like this.
So it'll tell you really specifically where to round to.
Oh.
I would suggest, if you're weary of rounding and truncation, if you're in the middle of your work, keep like a minimum of 4 decimal points, and then you're probably going to be safe. But like we know when we apply logarithms to things, like answers change really fast. Like if you truncate to the 10th place versus the 10,000th place, very different answers are coming up. So the best way for you guys to avoid truncation problems is to make sure you're typing it like this. So instead of computing the natural log of 0.083, which we already rounded, remember, and writing that decimal down and truncating it, and then computing the natural log of 1/2 and truncating that, like you're adding mistake upon mistake upon mistake, which is what truncation is. So it's always best if you keep things as accurate as possible. So bad news for us, that means fractions. So really, if I was like a superb scientist, I would have left this 0.0833 thing, I would have left it as 10 over 120 or 1 over 12. That would have been the most accurate way to write that. So, yeah, if we're talking about a lame problem on my pre-calc test and my teacher doesn't really tell me where to round and close enough is good enough, that's fine. But if you're like, sending someone into space, maybe watch out. If you're cooling my cup of coffee, I don't care. But if you're cooling my airplane part, I care. Yeah, one of those things. All right. That is the end of your notes. So good news. We have, oh my gosh, lots of time. Worksheet 10 is where we're going to start. Now, if you guys notice on worksheet 11, you already have, I hope, the whole back of it done. Worksheet 11B was an assignment from a long time ago. You were supposed to do the circled problems on 11B already, so that's done. Yay. Worksheet 10, however, you haven't done anything on it, and that's okay because we just learned it. The good news about worksheet 10, there's actually not a lot of questions on it. Like, it looks terrible, but if you notice every single question, because a lot of them are those Newton questions, they take up like a third of the page, so that's kind of rough. All right, worksheet 10. I'm going to try to hop around so we do at least one of every kind. All right, let's do that first Newton's Law question at the beginning of worksheet 10. And just so we're clear, your homework tonight, hopefully you're caught up, you have to do worksheets 10 and 11, and you have like 5 or so problems in the book. Okay, they're all applications like this. So Newton's Law of Cooling, of course we use the secondary formula, this guy down here, and this time we have a hard-boiled egg. Oh man, really changing it up here. The hard-boiled egg comes out of the boiling water. It is 96 degrees Celsius, so that's the initial temperature. And this time they plunk it into a cold water bath, which is what you're supposed to do to hard-boiled eggs, right? So this is the temperature of the surroundings. So this is T sub S. But just so you guys are aware, on your test, they changed it and called it T sub M for medium instead of surrounding. Sorry about that. 4 minutes later, I hate when they spell numbers. It always bothers me. I always miss it. That's your T. The temperature dropped to 45 degrees. So that is your final temperature for part 1. Remember, Newton's Law questions have part 1 and part 2. So for part 1, where we're trying to find K, all right, let's get this set up. Starting with final temperature, which is 45, minus the surroundings, which is 16. And then in the quantity, you have 96 degrees minus 16 degrees. And on your test, I would really suggest you guys just physically show the setup. Don't do any calculations until your second line, because if you happen to put like a number wrong in your setup, I can still kind of give you most of your credit for executing everything after that. Fine. And then e to the t is 4 minutes, so negative 4 times k, because I have no idea what k is. All right. Is that 29 equals 80 times e to the negative 4k power? And then you're dividing both sides by 80, and this is where I would just apply the natural logarithm to the fraction that you have there. And of course, when we apply it to the right side, beautiful things happen. So I need some calculation help here, guys. What happens when you apply the natural log to 29 over 80? Now, if you're really looking for some shortcuts on your work, because I know some of you like live for shortcuts, as far as showing work, what I do on my work, but that's because I've solved a lot of these, my next step I know is going to be to divide by negative 4, so I actually just do that. If that's too much, if that's like, no, because you're very new to these, that's okay. So remember, our k value should come out to something small and something positive, so please tell me that's the case. Is it something small and positive? Is it 0.25-ish? Okay, good. So that's part 1. Now we're going to use that constant of cooling, and we're going to change our final temperature. We want it cooled all the way down to 20 degrees. So that changes. So 20. We still are going to go back to the beginning of the problem. So they put it in that ice bath, which is 16 degrees. Then we're starting over the problem. So we're saying it came off the boiling water of 96 minus 16. And then this time, you know k is 0.25. So the t is what we don't know. So it's negative 0.25 times t. So that's a 4 equals 80. times e to the negative 0.25t. All right, so I know this is the moment where I'm going to be applying a natural log. I'm just going to sneak a natural log in right here. And if you want to try being the laziest person possible, like me, your last step is going to be to divide by negative 0.25. So if you truly, truly hate showing work and you want to make that as small as possible, that's about it. That's as much as you can get away with showing work without getting, you know, your teacher suspicious of you for copying. Okay, I want to see at least that much work. What'd you get for T? That sounds right. What was it? 12 minutes? Yeah, that works for me. Thank goodness we did the calculation. Now we know when we can eat our hard-boiled egg. See, wouldn't this have been perfect right before Thanksgiving? Y'all could have sat down and said, wait, I need to calculate something. You could have stuck the little thermometer in the turkey right when it came out of the oven, and then like a few minutes later, and then quick ran a calculation and be like, Ma, the turkey is not going to be cooled to optimal serving temperature until, and then you could have calculated it for her. That would have been perfect. Your whole family gets salmonella. Do you know how much pressure that is to cook a turkey for like 20 people? Like, if that turkey goes bad, y'all sick. It's a lot. All right. This is a really uplifting question. It's about homicide investigations and body temperature after you die, which is actually an application of this. So my CSI investigator people, you know, up there in Lawson's class, you should bring this up to him. Does he teach forensics still? I don't even know. Anybody in forensics now? Did you guys talk about this at all? You should. It's fascinating. And depressing. All right, maybe a nice project right before Christmas break. What did you do today, kids? We talked about what happens when, you know, bodies start to decompose. All right, so I'm going to leave that fun for you. Let's talk about this question here. Bears. What a cute question. All right, so bears in a wildlife conservation area. So, you ever heard the phrase, logistically speaking? Okay, so logistically speaking can mean a lot of things to a lot of people, but what we're going to interpret here is called a logistic growth formula. And at no point in your life do you have to know why it exists, how to come up with it, and you definitely don't have to memorize it. But this is the logistic growth formula. A, B, and R are positive real constants, cool, and they've been calculated through someone who knows more math than me even. So no way do you guys need to understand where this is coming up from. But think about this, guys. If you have, and this is a really good example for wildlife, if you have Rock Cut State Park, okay, you have a wildlife area, and if you let a certain species of animal kind of go unchecked, like deer, for instance, you know, there's ramifications on the environment based on how many deer are in the area, yeah? And while, if you don't think about it too hard, you might think, oh, well, there's no range stop to the deer. If the deer are left unchecked, then they're just going to keep, the population's going to grow and grow and grow and grow. Now, is that actually true? Logistically speaking, no, because there's only so many resources available to the deer. So when there's too many deer, or in this case bears, and there's not enough resources to go around, the population, like nature takes its course, and they don't all make it, or they stop breeding, basically, is what happens. So there is a cap to the population of your wildlife based on what sort of resources are available to them. So what we're going to do tomorrow is we're going to look at regression and logistic growth. And you're going to see this graph like kind of swoops up and then it flattens out. And that's the, like, they call it implied domain and implied range of a function. So in real life, the implications are if there's not enough resources, it's not going to grow anymore. It's going to cap out. So this is a bear population. They gave you the formula. You don't have to know anything about this formula other than there it is. And what I want you to do is I want you to get this typed into Y1. Now be careful and practice this, everybody, because there's a question just like this on your test. Make sure that whole denominator is in parentheses. And then the other thing I'm going to need you to do is to create your table set. I want you to put the independent variable into ask mode. So that means instead of giving you a bunch of automatically filled in x's, it's going to ask you what x's and you're going to type them in one at a time. So table set would be right above the window key, so second window. And change your independent variable, I think that's what they call it on there. Yeah, independent, change it to ask. Keep dependent as auto. So what they want you to do now is figure out the population of bears at various number of years. So 0 years in, 3 years in, 10 years in, and 30 years in. So one at a time, I need you to type those in for X, hit enter, and then it'll pop out the Y value at the end. So at the beginning of this problem, how many bears were there? And of course, round to the nearest whole bear if you need to. We'll talk about partial bears today. Is this a 15? And then 3 years later, you should get about 34. And then 15 years in, or 10 years in, excuse me, you get about 154. And then 30 years in, you get about 299. So somewhere in between 3 years and 10 years, the bear population surpassed 50. Now, my next question is, can you figure out what that time is? So what I want you to do for this next question, when will the bear population be 50? Let's use our graph. In Y2, why don't you put 50? And through our investigation, we just said like between 3 and 10 years, somewhere in the middle there, it hit 50 for population. So for window, can you have your X min and your X max set up from 3 to 10? And then we're going to use your favorite way to cheat, which is mine too, zoom fit. As long as you've set up a good X window, zoom fit will work really beautifully. Now what you should be seeing is a weird little curve thing, which we'll talk more about tomorrow, and then just a horizontal line. I need you guys to figure out where they intersect. Which is easy. If I'm going to make you do anything, intersect is the easiest one. So go to second trace, and then choose intersect, and then enter, enter, enter. There's a question just like this on your test. Oh, I'm sorry. And you should get about 4.45 years. And then it says, what's the max number of bears? So maybe before this discussion, you might have thought, well, there isn't a max number of bears because whatever, bears can do what they want. Not really. I mean, look at that curve. It flattens out, doesn't it? So you have a choice. You can either trace along the curve, or you could go back to your table and just plug in like a really large number of years, like put 1,000 years into that formula. And you should get, wait, let me guess, 300. Do you get 300? Or something that's really, really, really darn close to 300? Okay. That's what your function is approaching, a maximum number of 300 bears. So logistically speaking, in this environment, the bears population cannot go over 300. It just won't happen. Notice in the formula, the number 300 is the single number that's in the numerator. That happens to represent the logistical maximum of your function. So there's one easy question for you on that question. 300. All right. If I look ahead on worksheet 10, I want to quickly discuss this guy. Some of you have been in chemistry and you know all about the pH scale. So the pH calculation formula is, I think they call it the anti-log. Isn't that what you guys call it in chemistry? I don't know. There's teachers a few years ago who kept calling it the anti-log, which I guess is true. Other than in a chemistry class, I've never heard it called that. So the anti-log of the hydrogen concentration. Yeah, hydrogen ion concentration. So for these questions, they want you to first calculate the pH of the product and then determine whether it's an acid or a base. So this is the concentration of the hydrogen ion for lemon juice. Take a wild guess, guys. Lemon juice, acid or base? Yeah. Either way, you plug that into the formula. You're in your home screen of your calculator. You type negative common log of this number, and then you get a pH value on a scale of 0 to 14. So I don't know if your chemistry teachers would disagree with this, but this worksheet says 0 to under 7 is considered an acid, and then above 7 to 14 is a base. But if you're at 7, we're going to call that neutral, but I think most chemistry teachers like give you a little wiggle room around 7. I'll be honest, the lemon juice, the tomato juice, and the seawater are very clearly one or the other. It's not like none of those are neutral. So calculate the pHs, tell me if it's acid or base. You probably already know that question. Oh, maybe not seawater. Pretty sure you know whether seawater is an acid or a base, guys. But maybe not. I don't know. You figure it out. And then there's a couple more questions about calculating the hydrogen ion concentration. This requires a little PreCalc math, so set that up and try to figure it out. And then over here is a half-life question. We talked about that on the previous... Oh, this is worksheet 11A now. So here's what you're doing for homework, guys. I would start with the bookwork. So the bookwork it's just a few questions. I think it's page 167. I forgot the numbers, but it's right here. It's 37 to 42. So not a lot of questions. Start there. Then go back, maybe finish up worksheet 10, get some more examples of, I think there's another logistic growth on there, and there's another Newton's law on there. Worksheet 11A is all you should have to finish at that point. I know that feels like a lot to do, but they do go kind of fast. Now, unfortunately, I think some of you are playing the catch-up game. If you are also behind on your other homework, get unbehind, please. These are not easy things, and guys, we're running out of time. Like, it's almost December, which means things are shutting down real fast. So, good luck.